Hi, I'm Yixiao from Idaho National Lab. Today my talk is Transient kinetic characterization surface ocean species to understand steady-state performance of oxidative coupling of methane. Methane is a major component of shale gas and can be used as feedstock for high-value chemicals like ethylene, propylene, and benzene. We have abundant domestic shale gas resources. There are different ways to transform methane to high-value chemicals. As indicated here, OCM show high productivity in transforming methane to ethylene. This research has been intensively investigated since the 1980s. OCM has complex chemistry involving the gas phase reaction and the surface reaction. There is no consensus that in the active sites and the reaction pathway, and their different active sites have been proposed in the literature. OCM still challenged in achieving more than 30% of yield in the economic target area. Manganese sodium tungsten oxide silica is considered as a state-of-the-art catalyst. There is agreement that the CH4 activation on some reactive ocean species. However, the nature of the ocean species and their role in the reaction mechanism is much in controversies. There are many works on the OCM catalyst structure characterization. For example, XPS is a powerful technique to investigate different ocean species by looking at their ocean binding energy. And then, depending on the binding energy, they can be assigned to selective or non-selective ocean species. A lot of reported spectroscopy was done far away from the OCM reaction condition, like temperature condition, and low temperature might not be relevant since sodium tungsten oxide melts around 700 degrees C. Spectroscopy information usually contains the bulk or near-surface information, which might not well present the surface information. Recently, water addition was proposed to modify the surface ocean species and become more selective for OCM reaction. Then overall, the OCM has a challenge in catalyst characterization and it has a complex chemistry. In this presentation, 3 research questions will be answered. What is the role of catalyst composition? Why does one catalyst perform better than the other? And how to design an effective catalyst? 3 approaches will be used: decouple surface reaction from the gas phase reaction, and then we can investigate surface reaction separate from the gas phase reaction. In situ catalyst surface composition characterization under the reaction temperature condition, and build up a relationship between the surface oxygen composition and the OCM performance. In this study, we will use the temporal analysis product as the main tool, and the manganese sodium tungsten oxide as the state-of-the-art catalyst will be used. A short introduction on TAP, since it's not a common tool. TAP is a low-pressure pulse technique. Its major component including pulse valve, microreactor contains a tiny catalyst bed, mass bed, and extra high vacuum system. As the movie shows here, a gas molecule injected from the pulse valve, and it's randomly diffused through the reactor, and eventually the gas molecule will be escaped from the reactor and detected by the mass bed. The concept of TAP reactor is different from the flow reactor. It is a dynamic system. It can reveal more kinetic step rather than the rate-limiting step. It has well-controlled gas diffusion regime, which enables the separation of gas-catalyst surface interaction and gas-gas interaction. It has fast data acquisition system and high data resolution, enables study of short lifetime intermediates. Therefore, TAP is a powerful tool to investigate a complex reaction mechanism system. Let us start from the methane activation and C2 coupling. Different amounts of CH4 molecules were introduced into TAP reactor at 800 degrees C over the state-of-the-art manganese sodium tungsten oxide materials. Methane conversion and C2 yield is present here. In Lucian diffusion regime, when there is no gas and gas interaction, no methane conversion and C2 yield was observed. When we increase the pore size and the gas-gas interaction increase, we will see the increase in methane conversion and the C2 yield. Now, when we start to analyze the transient kinetic information in the Lucian diffusion regime, we find out that the methane experiences a reversible absorption process. As you can see figure here, red experience a positive followed by a negative. Overall, therefore, methane activation is reversible when there is only methane and the catalyst surface interaction going on. But methane can be irreversibly activated and converted to products out of Lewison diffusion region, where gas and gas interaction becomes significant. And we concluded here that CH4 activation is initialized by the surface reaction, and the C2 coupling happens in the gas phase. By posing CH4 and deuterium, or C2H6 and deuterium, we are able to investigate the activation product of methane and ethane. As you can see from the figures, both on the left and right side. On the left side, we can see that CH3D is the major product. And on the right side, you can see that C2H5D is the predominant product of C2H6. And therefore, we can conclude that CH4 activation is initialized by the catalyst and forming CH3, and CH3 either stay on the catalyst or dissolve in the gas phase. And C2H6 is formed when CH3 radical meet in the gas phase. C2H6 can further dehydrogenation, and which can be initialized by the catalyst and accelerated by the radical reaction. Furthermore, we investigate the type of ocean species for the methane activation. And in this experiment, CD4 and 18O2 were co-poses. And we can see that different water isotopes were formed. As you can see from the figure that D218O is much higher than the D216O, which indicated that CH4 is activated on some weakly absorbed ocean species. It's not from the lattice oxygen, and lattice oxygen actually is less active than the weakly absorbed ocean species. The co-posing of 13CH4 and 18O2 allow us to distinguish the type of oxygen for non-selective product for the CO2 and CO. As you can see, different isotope distribution, we can see that for the carbon monoxide, 13C18O is the predominant product of the carbon monoxide, and 13C16O2 is the major of the carbon dioxide product. And this result clearly suggests that the lattice oxygen played this significant role in the CO formation, and the lattice oxygen influenced a lot in the CO2 formation. Now, we know that the weakly absorbed oxygen species can exist during the gas phase oxygen activation process, and the concentration of this weakly absorbed oxygen species will affect the methane activation. In order to characterize the type of surface ocean species, we apply the methodology of pump flow experiment by using 16O2 and 18O2. The primary pose of 16O2 allows 16O2 to absorb on the catalyst surface, and then it can form different types of ocean species intermediates. And then a secondary 18O2 poses is injected. The exchange of 18O with 16O intermediate from the primary pose can be detected. The formation of 16O2 during the 18O2 poses can be ascribed to the existence of some diazo species, and the mixed isotope here can be contributed to the existence of monoso species. From the experiment, we can observe 16O2 and also mixed isotope formation during the 18O2 poses. However, their kinetic feature is very different, and also depending on the catalyst composition. For example, for this tungsten oxide, we only observe a single peak on the 16O2 and a single peak in 18O16O. When we add in the sodium into it, we can see that the second peak appears and with delay time. Further, when we increase in the manganese into it, for example, in this case 1% of manganese, and then we can see that even more delayed in the second peak. And different manganese loading will affect the different delay time on the second peak. However, for the mixed isotope 18O 16O, the peaks have an insignificant shift. Overall, this kind of pamphlet experiment showing that we can, in general, we have 2,16O2 desorption over the OCM catalyst, and 18O16O is more constant, independent on the catalyst composition. Therefore, the catalyst composition really influences a lot in the 16O2 formation kinetics. It's actually the kinetics of the diazo species on the surface. The next, we're going to study the steady-state OCM performance at 800 degrees C over different OCM catalysts. Overall, both figures on the top showing that methane conversion increase by increasing the gas residence time in the reactor. Especially at a low residence time, ethane is the primary C2 product. The conversion of C2H6 to C2H4 is there by increasing the residence time. C2 selectivity especially increase when the gas phase oxygen substantially decrease. Okay, therefore we can make a prediction. On the steady-state performance and also on the catalyst surface oxygen species composition. The y-axis information was obtained from the steady-state performance, and the x-axis information was from the 16O2 and 18O2 pamphlet experiment. The color bar represents the diazo species desorption peak time, and the diameter of the circles here is present the 18O2 conversion level. The 18O2 conversion is an indicator of oxygen activation efficiency or its oxygen activation ability. And this figure indicates that the higher ratio of diol to mono species, the higher the selectivity of C2C3 product. And also the higher ratio of diol to monosol species also lead to higher 18O2 conversion. That means higher oxygen activation ability. There is optimal diol characteristic desorption time for the optimal C2C3 selectivity. It's along between 0.22 second and 0.24 second. Therefore, we can see that the diol species are mainly responsible for the increased C2 selectivity during the OCM. Therefore, our conclusion is the role of the catalyst or catalyst composition in the OCM is going to activate oxygen, gas phase oxygen to the adsorbed oxygen species. And the adsorbed oxygen species activate the CH4 and forming C3 radical. C3 radical coupling in the gas phase. And the CO2 form mainly controlled by the surface process. C2H6 convert dehydrogenation to C2H4. And bulk or lattice oxygen is next active as compared to the weakly adsorbed oxygen species. Now, we can also explain why one catalyst performs better than the other, because different catalysts have different ratio of mono or diol species, and there is optimal surface residence time of the diol species correlated to the manganese loading. And regarding the effective OCM catalyst designing, the diol species must be the mainly responsible for the increased C2 selectivity during the OCM reaction. Therefore, increasing the diol species on the surface is the way to design the effective OCM catalyst. The significance of this work is we showing that the transient kinetic method can uniquely apply to studying the principle of OCM reaction and the catalyst characterization. It's going to help us to explain how and why a complex industry materials perform better than the other at the reaction temperature. And in the end, I want to acknowledge our funding agency and also our colleagues at our Transient Kinetic group in Idaho National Laboratory. Thank you.